All right, hope everybody's doing well. We're doing hypothesis testing, goodness of fit tests. And what we're going to talk about next is a test of independence. What we're really doing here, it's a special case, and we're just assuming that proportions are uniform across categories. Sometimes this is called a chi-squared test of independence. Usually what we're doing is we have two binomial or multinomial categories, like gender or favorite sport or favorite color. And we use a contingency table to display these. I'll show you one of these in a second. But our null is always going to be these variables are independent, meaning that one has no effect on the other, and or is not correlated with the other. And then our alternative is going to be that these variables are related; they're not independent. So, step one, stating our once you figure out that this is a test of independence question, which you might when it says something like test to see whether these two things are independent. Um, Usually that's pretty straightforward. Step one, figuring out what the variables are, it goes pretty fast. Okay, now what might be an example of this? Well, let's work through one. Okay, so let's imagine we do a survey of 255 people. We're asking people their favorite sport by gender. What we really are doing is we're just giving them a card that says, "What's your favorite sport?" And the options are football and golf, I think is what I have here. Let me see. There we go. What's your favorite sport? Football or golf? And what's your gender? Male or female? Okay, now we ask 255 people, and this is what we find. Actually, let me get rid of these grid lines. There, that's much prettier. There we go. So these are our results. Disappeared. There we go. 75 people are male and like football. 65 people are male and like golf. 45 people are female and like football. 70 people and female like golf. And as I said before, our null is always going to be that the same percentage of people who like football are male as people who like golf, or the same percentage of men like football as women like football. That the percentages do not vary across these two categories, right? That they're not related. Okay, so the way that we test this, much like when we did before, is we're gonna need a test statistic. So if that's true, if the null is true, if these variables are independent, then chi-squared, which in this case is equal to the sum across rows and the sum across columns of the observed frequency for row R in column C minus the expected frequency for row R in column C squared divided by the expected frequency for row R in column C. Under the null, this will have a chi-squared distribution with m minus 1 times n minus 1 degrees of freedom. That looks a little messy. But just like before, we have our observed frequencies already, right? These are observed frequencies. So for row 1, column 1, our observed frequency is 75. For row 2, column 1, our observed frequency is 45. Right now, we already know we can figure out how many degrees of freedom we have. Turns out we have two categories in the rows. So we have male and female. And we have two categories in the columns. So there's going to be 2 minus 1 times 2 times 2 minus 1, which is going to be 1 times 1, which equals 1. Okay, so we're going to have 1 degree of freedom. That's all we have left. That's fine. That's often, that's the simplest case of a test of independence. You just have pairwise comparisons. Okay. Now, in order to do this, what we need to do is so we have our FRCs. In order to calculate this, we're going to need our expected values. So, how do we do this? Well, if they're independent, then this will be true. Let me write it out. Let me pick a different color quick. If they're independent, then the frequency we'd see for row R and column C will be the row R total times the column C total divided by the sample size. Because it turns out that that's just That's just multiplying proportions. There's not, yeah, it normalizes our proportions if we do it this way. So the same proportion of women prefer golf to football as men, the same proportion of sports lovers prefer football or male as the proportion that are female. So if they are independent, then the number of men who prefer football should look like this, right? We'll just do an example to try to show you what it would look like. So the expected frequency for men who prefer football, row 1, column 1, is going to be row 1 total, 140, times column 1 total, 120, over 220, or 255, sorry. The sample of 255, which you can get by adding these together. Now, if you plug that in, for 140 times 120 divided by 255, you're going to get 65.88 something. It gets long if you really go along with it. Oops. Let's see if I can. Okay. Well, I'm going to go to a new page so that I can just draw this whole contingency table up. But the way that it'll work then is we're going to draw a new table that looks like our old table, except it has the expected values in here, right? So 65.88 is what you get for men in football. If you do it for men in golf, you'll find 74.11 female, and 54 in female golf 60. If you add these up, you should still get the same totals, but now the proportions are equalized. So that's our expected frequency table. Okay, so where do we go from here? Well, let me copy this one down so that we can make use of it again. And I should label these so we have access to them without being wrong. Oops-a-daisy. Okay. Is there an easy way to do this? I'll just copy it like I did before. Okay. So what we want to do then, once we have these two tables, is we want to convert our contingency table into a regular table. So we have these rows and these columns. I just copied and pasted a bunch of stuff. Don't worry. Actually, I'll hide these for now so that we can talk about them when we need to. That's not good. No. There we go. That's good. Okay. So we can pull these from our actual tables. When we asked people, we had 75 people who were men and preferred football, and 45 people who were female and preferred football. That was row 2, column 1. Now, if independence is true, that implies that these are the expected rows. And I used the multiplication formula to get this. Okay, now if you remember our test statistic, which looked a little complicated, but it's nothing so outside what we've worked with before. It looked like this. Chi squared equals the sum across rows and the sum across columns of the observed frequency for row R and column C, F sub RC minus E sub RC squared over E sub RC. You might see this sometimes as the rows indexed by I and the columns indexed by J. So you might see that sometimes where the index is just different. It doesn't change anything, right? The letter you use does not matter. And remember, this is distributed n minus 1 times n minus 1, where that's the number of rows. And this is the number of columns. This is all in the notes that are also available on the Blackboard site for those of you who are taking the class. And for those of you who are not, well, now you know. Okay, so in order to calculate this, though, we're going to need to do this math. So what do we have? Well, make this visible to you. You can see that this is commonly the way that it'll work when you have two categories, right? We're just shifting things from one place to another. The difference is the same, but the signs change. We square that and then divide by ERC. It gets a little messy. I mean, just doing it by hand, it's going to take some doing. But you're going to get values that look like this. Now, once you have this table calculated all the way across, all you have to do is add these together, right? Because we're adding across rows, we're covering both rows and both columns. So we're just going to add these together. Just 1.2618 plus 1.5361 plus 1.1216 plus 1.3654. And if you do that, you're going to get, I can just do this. You're going to get chi squared, why is this caps lock? There we go. Chi squared equals 5.285. And under the null, we have if you remember, we have a distribution chi squared with 1 degree of freedom. Right, so we can draw that curve if we want. It's going to look something like this. only not really, but that's good enough. Chi-squared, 0's here, and we have a test statistic at 5.285. Okay, so is this, so, oh, yes. Much like every goodness of fit test, what we're testing to see if the differences are big. If they are big, we'll reject the null. If they're not big, we will not reject the null. And so it's always an upper tail test. Goodness of fit tests are always upper tail tests. So is this big? Is 5.285 big? Well, we need to go to our chi-squared table. Here it is. We have 1 degree of freedom. And what we're looking for is the two test statistics that fall on either side. Now, our chi-squared was 5.285. And so we're talking in between 5.024 and 6.635. That means that our area in the upper tail is going to be between these two, 0.01 and 0.025. Because it's an upper tail test, we are going to just care about that. That's going to be our p-value as well. So 0.01 is less than our p-value, is less than 0.025. Now, if we chose alpha in the beginning, which we didn't, because I've been slacking on that, then we would know what to do. I'm going to say that alpha is going to be 0.05 because it usually is. And in that case, our conclusion would be to reject the null because our p-value is less than alpha. Right? Our p-value is less. That's a greater than sign. Yeah. It's upside. Anyway, you get the idea. We'll reject the null. Our null hypothesis was that they're independent, that there's no difference in sport preference across gender, or that there's no difference in gender across sport fans. And we can reject that. In this case, it looks like men are more likely to prefer football and women are more likely to prefer golf. It's just made up data. I just made it up, so you can't draw any real conclusions about this. But it does look in this data like gender is correlated with favorite sport. So we have another minute or so. I'll just show you how we would calculate this in Excel. If I can copy this over. At least we can, yeah. So let's see. It's from a different problem. There we go. So let's delete this. Delete this. I'm going to assume that you guys got... So we got our observed frequencies and our expected frequencies. Once we do that, we can subtract these. And you'll get... This is how I got these values, right? So this is F RC minus E R sub RC. What we want to do next is square that. Equals E2 squared. I'm just holding Control D to fill down. And this is just going to be this quantity squared. Now we're going to want to divide this by the expected value, by the ERC. So if we divide this by the expected value, it's 83.13154 divided by 65. Fill this all the way down, and those are our values for each row and column, right? To add these up, we can use the sum function, add them all up, 5.285. We know how many degrees of freedom we have, so we can do this just with a chi distribution. Equals chi dist, and as you see, it returns the one-tailed probability of the chi-squared distribution. We're going to want our x, or value of the chi-squared, and we have 1 degree of freedom. It's 0.21. Now, if you remember, we bounded it before as being between 1% and 2.5%, and it is. It's 2.1%. So with Excel, we can figure out exactly what the distribution is, and that's how you do it. That's what you need, and that's how you find the answer. You need to know what to do with that p-value. You reject, right, because that's less than alpha. But that's how you do tests of independence. Okay, there's a few steps. The first is that the null is always independence. And the alternative is always a lack of independence. You get your, this is your observed contingency table. And then you have to use this formula here, the E formula, to build your expected contingency table. And then you fill in a table like this, convert it to kind of a goodness of fit table, and work your way through it to come up with your value of the test statistic. From there, it's just like every other hypothesis testing problem we've done. But the data generating process takes a little while. So I hope that's been useful. If you have any questions, please shoot me an email at jjdelaney@ualr.edu or leave a comment, and I'll try to get to it as soon as I can. Hope to see you guys again soon. Thanks. Bye.